The conversion of matter directly into energy is the main power source for stars like our Sun. In this question, we'll figure out how much energy the stars in your constellation can generate this way throughout their lifetimes. Once again, we're going to follow the math worksheet to solve this problem. The first two boxes ask what you're trying to find and what you know. As with most of these questions, what you're trying to find is simply the title. Which star in your constellation has the most mass energy available to it, and which has the least? Mass energy is the energy produced when matter is converted directly into energy. We rarely have experience with mass energy in our daily lives, but it's very important inside stars. The nuclear reactions that power a star like the Sun involve turning matter into energy. In these reactions, only a small fraction of the mass is actually turned to energy. The rest is simply converted from hydrogen into helium. So given that only a small fraction of the star's mass is turned into energy, we can calculate how much energy is released in this process. Later on in the course, we'll use this information to figure out how long these stars can continue shining. The question also tells you two pieces of data that you'll need to know. One is the portion of the star's mass that is converted into energy, 0.07%. We'll need that in our calculation. The other is the amount of energy the Sun has available to it this way, 1.26 times 10 to the 44th joules. This will let us compare the energy of the stars in your constellation to the Sun's total energy. There are a couple of parts to the prediction in this question. The first part is simply asking which star will produce the most energy and which produces the least. Make sure you're looking at all the stars on your list, not just the ones with common names and not just the ones that have distances listed. Since we're dealing with mass energy, the amount of energy the star has is going to depend on its mass, so you should be using the mass information to make your prediction. The other part of the prediction is asking how this energy will compare to the Sun's lifetime energy production. Once again, the masses are what is important here, so you should be comparing the masses of your stars to the mass of the Sun. Notice that the masses in the table are given in solar masses, and that the Sun has a mass of 1 solar mass. Remember that when you give your predictions, you need to explain why. That's what shows that you have an understanding of what the question is asking and what physically is going on here. Now we can set up the calculation part of the problem. The first step is to write down the formula. Since we're trying to find the mass energy, we need to use Einstein's mass energy formula. E equals mc squared. In this formula, E is the energy produced, m is the mass that disappears, and c is the speed of light. Notice that the speed of light is the only part that is squared, not the mass. This equation tells us what numbers we need to look up. For the masses, we'll need to have the masses of the stars, so you should write down the masses of any stars you'll be calculating. Make sure you include both of the stars from your prediction. You'll also need the speed of light, so make sure you look up that number. It's given in the textbook and the online lecture on motion and energy. Make sure you've got this speed in units of meters per second. If it's in any other units, you can convert them, but it's usually easiest just to start in the right units here. In this problem, we've got several units involved, but only one of those is going to require converting. The energy in our answer will be given in joules, but remember that a joule is just a kilogram meter squared per second squared. So really, a joule is just a mass, distance, and time unit combined. The masses of the stars are given in solar masses, but we've already seen that joules have a mass unit of kilograms. So we'll need to turn the stars' masses into kilograms to match. Let's try this for the case of a star with a mass of 8 solar masses. When we look at the key that comes with your constellation table, we see that 1 solar mass is 2 times 10 to the 30th kilograms. So 8 solar masses times a conversion factor of 2 times 10 to the 30th kilograms divided by 1 solar mass gives 1.6 times 10 to the 31 kilograms. This star is significantly larger than the Sun, so the number of kilograms should be more than the Sun's, and that's what we see since the exponent is larger. You'll need to do this conversion for each of the stars you're calculating. We're finally ready to calculate how much energy these stars can generate in their lifetime. We start by listing the formula again, this time with the values of the mass and the speed of light. We'll continue using the 8 solar mass star from the previous slide. However, remember that we can't use the entire mass of the star. Only 0.07% of the mass is turned to energy, so we need to multiply by that 0.07%. Since taking the percentage is like dividing by another factor of 100, we use 0.0007 here. Also, notice that we've got the speed of light squared. At this point, we do what the equation says. First, we square the speed of light to get 9 times 10 to the 16 meters squared per second squared. When the speed is squared, the units are squared with it. Now we just multiply through all of the terms. This gives us the total energy. The units are kilograms meters squared per second squared. But as we've already seen, this is the same thing as joules. Notice how big that exponent is. Remember, this is the total energy produced by a star 8 times as big as the Sun over its entire lifetime, so you should expect a big exponent. You should do this calculation for all 3 of the stars you selected. The last step in the calculation is to figure out how many times bigger or smaller this is than the energy produced by the Sun. To do this, just divide the energy you just calculated by the energy of the Sun. Notice that when you do this, the answer is much smaller. If you're getting a bigger exponent here instead, that tells you you're not entering the exponents in your calculator correctly. Make sure you're using the EE or EXP key and don't put in extra times tens. The answer here has no units. It's simply 8 times as much energy as the Sun produces. Remember to decide if your results match your prediction and decide if the answer seems reasonable. As usual, there are 3 possibilities. Either everything matches and the answers are reasonable, or else you have a mistake in either the calculation or the prediction. If everything matches, you should say that. If it seems that the results from the calculations don't look right, then see if you can find the error. It's okay to ask for help if you're not finding it. If it's really too late and you need to turn it in, at least make sure you say why you think there's something wrong with the result. Working through the example here can help you figure out if you're doing something wrong, and give you a better idea of what the right answer should look like. If the problem is in the prediction, you should explain what you should have predicted and why. But only do this if you're really convinced that your calculations are right and what they're saying makes physical sense. Once again, if you're not sure, just ask.